true projects. In this video, we are going to explain about the project entitled as Cyber Attack Prediction from Traditional Machine Learning to Generative Artificial Intelligence. So, before getting into the video, let me give you the brief description about the project. Cyber attacks are becoming more complex every day and predicting them is crucial. In the beginning, traditional machine learning models like decision tree and random forest were used to detect the attacks. They analyzed historical data and learned from past threats, but they struggled with new or unseen attack. Then came deep learning, using neural networks such as CNN and LSTM to automatically learn patterns in massive amount of network data. These models improved accuracy but still required large data set and lacked transparency. Coming to the abstract states that the growing complexity of cyber threat posed serious risks to individuals, organizations, and nations, with cybercrimes like hacking, phishing, and data breaches causing significant economic and social damage. As traditional security system struggles to keep pace, artificial intelligence has become a powerful force in strengthening cybersecurity. AI-driven methods such as machine learning and deep learning help detect and predict attacks by analyzing vast amount of data and identifying unusual patterns. Explainable AI enhances trust and transparency by clarifying how AI models make security decisions, while natural language processing improves the analysis of phishing emails, threat reports, and other text data. The latest advancement, generative AI, enables the creations of synthetic threat data and realistic attack simulations, allowing security systems to anticipate and defend against emerging threats. Together, these technologies represent a shift from reactive defense to proactive, adaptive, and intelligent cybersecurity, building a safe and more resilient digital future. Coming to the existing system, most current cybersecurity systems depends on traditional defense methods such as signature-based detection, rule-based firewalls, intrusion detection systems, and antivirus software. Although these tools are effective and recognize known threats, they fall short when dealing with new, unknown, or evolving attacks like zero-day exfoliates and advanced persist threats. Because they rely on predefined rules and static patterns, this system tend to be reactive rather than proactive, responding only after an attack has been identified. Furthermore, their limited ability to process and analyze large volumes of complex data in real time often leads to delayed detection and slower response time. As a result, in today's rapidly evolving digital environment, traditional cybersecurity mechanisms are proving increasingly inactive for combating modern, sophisticated cyber threats, underscoring the urgent need of AI driven adaptive security solutions. Coming to the proposed system or base paper work, the proposed system represents a comprehensive, practical implementation of an AI powered cybersecurity framework designed to detect and analyze malicious network activity. It begins with a robust data pre-processing pipeline that prepares the CI/CD 2017 dataset by cleaning, normalizing, and encoding the raw network traffic data to ensure consistency and quality. Feature engineering and selection techniques are then applied to extract the most relevant attributes, improving both model efficiency and accuracy. The system incorporates a broad range of AI models across machine learning, deep learning, and generative AI, allowing for extensive experimental and performance comprehension. These models are trained using a unified workflow that standardizes evaluation and ensures fairness across algorithms. To address the need of transparency in cybersecurity, the system integrates explainable AI tools such as LIME and SHAP, enabling users to understand why a particular prediction was made and which features contributed most. The final component is a Flask-based web framework application. Overall, This proposed system transforms theoretical AI concepts into a fully deployed real-world cybersecurity solutions. Coming to the dataset was collected over a period of 5 days in a controlled environment using realistic network configurations, user behaviors, and background traffic. Each record includes features such as flow duration, packet length, protocol type, and statistical characteristics of network flow, allowing for both low level and high level analysis. The CI/CIDS 2017 datasets provides both raw network traffic PCAP files and pre-processed flow based data CSV files, making it suitable for various types of research including feature selection, anomaly detection, and machine learning model evaluation. Due to its diversity, realism, and labeled nature, CICIDS 2017 remains one of the most widely used datasets in cybersecurity and network intrusion detection research. Coming to the extinction introduced in this work significantly advances the capabilities outlined in the base paper by moving from conceptual analysis to a fully practical implementation. First, a diverse set of AI model was developed covering machine learning, deep learning, and generative AI, enabling a comprehensive evaluation of different approaches for cybersecurity threat detection. To ensure transparency and trust in these models, explainable AI techniques such as line and sharp were integrated, providing visual insights into feature importance and model decision making. This system was further extended through a deployment of all trained models into a Flask-based web application, allowing users to interact with the system in real time and obtain instant threat predictions. Additionally, the entire workflow was designed as an end-to-end AI-driven cybersecurity pipeline encompassing data pre-processing, model building, explainability, and real-world deployment. Overall, these extensions bridge the gap between theoretical research and practical application, demonstrating how AI can be effectively implemented in operational cybersecurity environments. Coming to the flow of the work, firstly, we need to import the packages. In this step, all the required Python libraries such as NumPy, Pandas, Matplotlib, Scikit-learn, TensorFlow, and Keras are imported to handle the data pre-processing, visualization, and model deployment. Next, exploring the dataset. We used the CICIDS 2017 dataset, a benchmark dataset for intrusion detection. It contains real network traffic with both normal and malicious behaviors, which helps in building accurate and realistic AI models. Next, data pre-processing. Before model training, we clean and prepare the dataset by removing null values and duplicates, then apply label encoding to convert categorical data into numerical form, ensuring it's suitable for model input. Next, data visualization. Visualization helps us understanding the data patterns. We plot the distributions of classes, outcomes to see class balance and generate a correlation matrix to identify relationships between different network features. Next, feature selection. Using principal component analysis, we reduce the dimensionality of the dataset, keeping only the most important features. This step improves computational efficiency and model performance. Next, split the dataset. The dataset is divided into 80% of training and 20% of testing sets to evaluate model performance on unseen data and prevent overfitting. Next, normalizing the data. Normalization is done using standard scalar, which scales all features to a similar range, improving the learning speed and stability of AI models. Next, we deploy multiple AI models for comparison, like ML models, DL models, and generative AI models. Next, we have model evaluation. Each model is evaluated using classification reports, confusion metrics, and ROC curves to measure how efficiently these classification, normal, and attack traffic. Next, model comparison. We compare all models using accuracy, precision, recall, and F1 score. These results are presented in comparison graphs to easily visualize which model performs best. Next, save the best model. Once the best performing model is defined, it is saved for deployment and further predictions. Next, explainable AI visualizations. Using line and shape, we visualize feature importance and understand how each model makes its prediction, ensuring transparency and trust in AI decisions. Coming to the front end, the Flask framework is used to develop the web-based interface with registration and login features, supported by an SQLite database. Users can input feature values to the front end, which are pre-processed and passed to the trained model for the real-time prediction. The final result indicates whether the traffic is normal or an attack, is displayed instantly to the user. Algorithms used are ML models, DL models, and generative AI NLP models. In ML models, we used decision tree, random forest, extra tree, logistic regression, naive Bayes, and voting classifier. In DL models, we have used DNN, CNN, LSTM, CNN plus LSTM, CNN plus LSTM plus GRU. In Gen AI NLP models, we used VAE, GAN, and DIS GPT-2. Coming to the requirements, we have hardware requirements and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements, application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, deploy and test your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Template folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to the front-end logic. It could include code written in Python that handles server-side operations such as pre-processing user request, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb files. This is a Jupyter Notebook file which contains a combination of codes, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store user information. Coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the link provided by the framework and paste it in any web browser. I prefer Chrome. Now, the home page of the project should be displayed in the browser. This is a front-end built using the Flask framework. In this page, we have Home button and Sign Up button. Now, click on Sign Up button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, contact number, and a password. Then, click on Create an account so that All the given details are stored in signup.db and the login HTML will be opened, where you need to access the application by username and password. Then click on sign in so that the prediction page has been displayed. In this, we have home button, prediction button, data visualization button, notebook button. In notebook, we have ML and DL notebook and generative AI notebook. Then sign out. So firstly, we need to click on predict button. Then the prediction form will be displayed where you need to enter the network traffic features to predict potential cyber attacks. The network traffic features are given below. So as we have 7 attacks like benign, bot, DDoS, DOS Gold Eye, DOS Hulk, DOS Slow HTTP test and pot scan. So we need to give the input details and predict each attack. So first, the active minute will be 0. Forward PSH flag is 0. So first, let me give all the inputs to predict the attack. Now, click on predict cyber attack. So, the given inputs are pre-processed and the output has displayed benign, which means safe. The confidence score is 99.99%. The description is given as no malicious activity detected. It's a normal network traffic. So what are the immediate actions required are given below and the safety measures are given below. Next we have make another prediction or view visualization. So we'll make another prediction by giving the different input values. After giving the new values, now click on predict cyber attack. So the given inputs are pre-processed and the attack is of bot, which means it's a critical attack. The confidence score is of 54.64%. The description is given as botnet activity detected. This indicates compromised devices are being controlled remotely. And here we have the immediate actions required and the safety measures. And click on make an other prediction. Again, we can give some other values to predict an other attack. After giving the other values, now click on predict cyber attack so that the given inputs are pre-processed and displayed as DDoS attack, which is high. The confidence score is 99.98%. The description is given as distributed denial of service attack detected. Multiple sources are flooding your network. So here, what are the immediate actions required are given below and the safety measures are given below. And let me give you another prediction. So after giving the other values, now click on predict cyber attack. So for the given inputs, it detected as DOS Hulk, which is high. The confidence score is of 69.1%. And the description is given as Hulk DOS attack detected. HTTP jet flood attack overwhelming web servers. And here we have some immediate actions required and also the safety measures to be taken. And now we can predict another prediction. After giving the other values, now click on predict cyber attacks. For the values which you have given, it is detected as DOS golden eye detection. It is high and the confidence score is of 46.65%. And the description here given as golden eye DOS attack detected. HTTP flood attack targeting the web servers. Here we have some immediate actions required and the safety measures given below. Likewise, we have benign, bot, DDoS, DOS GoldenEye, DOS Hulk, DOS Slow HTTP test and pot scan attack. Now, click on data visualization. Data visualization means representing the data in graphical or visual format such as charts, graphs, maps or dashboard so that patterns, trends and insights can easily understand. So firstly, we have sample outcome graph. This graph presents the distribution of different traffic classes in a network intrusion data set, illustrating a strong class imbalance. The benign class overwhelmingly dominates the data set with over 1.5 million samples, while attack category appears in much smaller quantities. Among the attack, DOS Hulk and DDoS have the largest count around 170K and 128K respectively, followed by pod scan with about 90K samples. Other attacks such as DOS Golden Eye, DOS Slow Rose, and DOS Slow HTTP test appears with only a few thousand samples, whereas rare attacks like bot have extremely low count, sometimes only a few dozen or fewer. Overall, the chart highlights a highly skewed data set where benign traffic and a few types of attacks dominate, which has important implications for training machine learning models, especially the need to address class imbalance. Next, we have PCA explained variance ratio graph. This graph illustrates the cumulative explainable variance ratio obtained from applying principal component analysis, showing how much of the data set's total variance is captured as the number of principal components increase. Starting with the first few components, the explained variance rises quickly, indicating that these components capture the most significant structure in the data, reaching around 60% by the seventh component and suppressing 70% by the 10th. As more components are added, the curve continues to climb but at the slower rate, eventually nearing 88% with 18 components. Overall, the plot demonstrates diminishing returns. While the initial components contribute heavily to explaining the variance, additional components providing only incremental improvements, helping determine an optimal balance between dimensionality reduction and information retention. Next, we have variance explainable by each PCA components. This graph shows how much variance each individual principal component explains, alongside the cumulative variance across all components. The blue bar represents the explained variance ratio for each component, revealing that the first few components capture the largest share of information. Most notably, the first component explains over 20% on its own, with subsequent component contributing progressively smaller portions. The red dotted lines represents the cumulative explained variance, which risk quickly at first and then more gradually reaches roughly 88% by the 18th component. Overall, the chart highlights that while the first several components hold most of the dataset meaningfully variability, many additional components are needed to approach full variance coverage, helping guide decisions on how many components to retain for dimensionality reduction. And next we have confusion matrix and ROC curve. This figure shows the performance of voting classifier combining random forest, light GBM and XGBoost on the multi-class network attack dataset. The confusion matrix on the left illustrates that the model achieves extremely high accuracy across nearly all classes with very large correct counts along the dimensional and only small pockets of misclassification, mainly between benign traffic and few attack types. Classes such as DDoS, DOS Golden Eye, DOS Hulk, DOS Slowris, and PodScan are detected along perfectly with minimal errors. The multi-class ROC curves on the right further confirmed the model's strong performance, with most classes achieving an AUC close to or equal to 1.0, indicating excellent separability. Only the bot and infiltration classes shows slightly lower AUC values around 0.99. Overall, the model demonstrates expectational capability in distinguish between benign traffic and various attack categories. And next we have accuracy graph. This bar chart compares the classification accuracy of several machine learning and deep learning models on the same data set, revealing clear differences in performance. Traditional tree-based models such as decision tree, random forest, and extra tree classifier achieves very high accuracy, close to 1.0, while logistic regression performs moderately and Gaussian naive Bayes performs significantly worse. The ensemble voting classifier reaches near perfect accuracy, matching or suppressing most standalone models. Deep learning architectures including DNN, CNN, LSTM, CNN plus LSTM, and CNN plus LSTM plus GRU also delivers strong results, all approaching perfect accuracy with the hybrid CNN plus LSTM plus GRU model achieving the highest performance among them. Overall, the graph highlights that both ensemble models and advanced deep learning hybrids produce the most accuracy predictions. Next, we have precision graph. This bar chart compares the precision scores of several machine learning models, showing how accurately each model identifies positive cases. Traditional models such as decision tree, random forest, and extra tree classifier achieves perfect or near perfect precision, while logistic regression and Gaussian naive Bayes perform slightly lower. An ensemble voting model combines RF, light GBM, and XGBoost also reaches very high precision. Among deep learning approaches, DNN, CNN, LSTM, CNN plus LSTM, and CNN plus LSTM plus GRU, precision remains constantly strong with the hybrid CNN plus LSTM plus GRU model achieving the highest score. Overall, the graph shows that most models perform expectationally well, with deep learning hybrids and tree-based algorithms leading in precision. Next, we have recall graph. This bar chart illustrates the recall performance of various machine learning models, showing how effectively each model identifies all actual positive cases. Most models, including decision tree, random forest, extra tree, logistic regression, and ensemble voting model, and all deep learning models, achieve very high recall, closer to or 1.0, meaning they rarely miss positive instance. In contrast, Gaussian naive Bayes perform noticeable worse, with a much lower recall, indicating a high number of false negatives. Overall, the graph highlights that deep learning architectures and tree-based models are strong at capturing all true positives, while Gaussian naive Bayes struggles significantly in comparison. Next, we have F1 score graph. This bar chart presents the F1 scores of different machine learning models, reflecting the balance between precision and recall for each model. Most models include decision tree, random forest, extra tree, logistic regression. The ensemble voting model and all deep learning architectures achieve very high F1 scores, closer to or 1.0, indicating strong overall performance in correctly identifying positive cases with minimal errors. Gaussian naive Bayes, however, shows a much lower F1 score due to its weaker recall and precision, highlighting its difficulty in handling the dataset compared with other models. Overall, the graph shows that both tree-based methods and deep learning hybrid performs expectationally well, with the deep hybrid models achieving the highest F1 scores. And next we have explainable AI SHAP graph. This SHAP summary plot shows how each feature contributes to a machine learning model's prediction by displaying the distribution of SHAP values across all samples. Features are listed vertically in order of importance, with those never the top having the greatest influence on the models. Each point represents a single data instant, and its horizontal position indicates whether the feature pushed to predict higher or lower. The color reflects the feature values. Red equal to high, blue is equal to low. So you can see how high or low values tends to affect the output. Overall, the plot helps explain which feature matters most and whether the high or low values increase or decrease the predicted outcome. And then we also have cyber attack Gen AI data visualization graphs. So firstly we have reconstruction error distribution graph, and next we have VAE reconstruction error ROC graph, and then we have real versus synthetic graph, and last we have VAE training loss graph. And finally, click on sign out. So this project demonstrates that combining traditional machine learning techniques with emerging generative AI approaches significantly enhances the accuracy, adaptability, and interpretability of cyber attack prediction system. While classical models provide strong baseline performance and reliable detection using structured network features, generative AI adds the capability to learn deeper patterns, stimulate attack scenarios, and improve model robustness against evolving threats. Together, these models create a more intelligent and proactive cybersecurity framework capable of identifying sophisticated attacks earlier and more efficiently. So, this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.